All right. Hello, AP Chem Squad. Wish you all a very, very happy new year. Hope you all had a relaxing holiday break. So, in the new year, we are going to start with chapter 14, which is going to be your unit 6. And unit 6 is going to be kinetics and equilibrium. And here we are going to talk about kinetics. This is the first time you're going to be learning about this topic. So, I'll really recommend everybody taking notes, pausing the video and doing the flip problems as they're recommended, and do not move it at a speed of 2 or something when you're watching the lesson. I don't think so. It would be very helpful. And everybody, please do the problems as you watch them. So go gather your stuff, get your packet, pen, a quiet place, and let's dive into a new topic in the new year. And I'm sure you guys will do amazing. All right. So Chapter 14, Chemical Kinetics, the rate of chemical reactions. Here are the 7 topics that we will be looking as we will learn the different topics in kinetics. And I'll be dividing the lesson into 4 different videos. So it is important to understand over here the difference between kinetics and thermodynamics. What we are going to focus is on kinetics, and kinetics is going to help us understand how long will the process take. That means, and it also depends on the pathways, right? So kinetics is going to look at the pathways, that how a reactant is going to take different steps to go to the product. Sometimes it could be 1 step, 2 step, 3 steps, or many steps. While thermodynamic is only focusing on will the reaction occur. And so it is only dependent on the initial state, that is your reactant, and your final state, which is your product. So it's important that we understand the difference. We'll be learning about thermodynamics later on in our unit 7. So let's proceed with kinetics. First goal is to learn to calculate the average rate of a reaction from the concentration and the data and the time data. And we are going to relate the rate of disappearance of a reactant or the formation of the product in a chemical reaction. So let's see how we're going to do that. So in order to study and understand this, what we are going to do is we are going to see and figure out the rate of disappearance of a reactant. How fast is the reactant disappearing? One way to look at it is, if you look over here, the blue color, as the blue color disappears, we know that the reactant is being used and the product is being formed. So we are able to look at it, but every reaction does not have a color. So we would have to look at different data as to look at the change in the concentration. We are also going to focus on mechanisms, understanding the sequence of steps, how the sequence of steps help us decide what is making this reaction slow or fast. So we all have seen chemical reactions. Some chemical reactions are very fast, right? So if you have ethanol and you start the reaction is very fast. Rusting of nail, it is a very slow reaction. Formation of a diamond is a very slow chemical change, right? So all these, what is making some reactions go so fast while some reactions are moving so slow? So we are going to try to understand all those steps that are involved to help us understand why some reactions are fast and why some are so slow. A reactant over here, let's say A, is changing over time with respect to B. So A is representing everything in black color. So if you look over here, we have, to begin with, we just have reactants. As the time passes, we have some product that is formed and the reaction keeps going. So the negative sign over here is, so the negative sign is just saying that it is measuring the disappearance. So disappearance is given by a negative sign. So the rate of disappearance of A with respect to time is your rate. Or you could look at the rate of appearance. Therefore, there is no plus sign, because if you're looking at how much product is being formed, then we say it is the appearance of it. But we are going to be measuring the amount of disappearance of A with respect to time rather than looking at the appearance of B. Okay, so if you look over here, we are going to start with a very high concentration or amount of A. As time passes by, the concentration of A decreases with time while the concentration of B keeps increasing with respect to time. But it is important to see that we will still have some reactant and product always present, and reaction is really not stopping. Now, rate. So as I said, what is rate? The rate of appearance or disappearance is measured in unit of concentration. Concentration means molarity, which is moles per liter over time. And if you all remember, molarity is given with lowercase m. So it is molarity m over time. And so it is m over s. And when it comes over, this is the unit of rate. Okay, the time could be in seconds, time could be in minutes. So it is important that you understand molarity. The other thing is molarity is going to be given in square box. This means it is a concentration. So if it is given A, it means it is a concentration of A. Now, there are three different types of rates. We are going to talk about the initial rate, as the word suggests, average, and instantaneous rate. So if you look at this graph, we have this bromine and formic acid over here, okay? And with time, we are looking at the concentration of bromine changing over time, and the graph is plotted over here. Now, if you wanted to calculate the initial concentration, you could just look at the initial time and you'll be able to do no reaction has started at this point. If you have to calculate the average rate, the negative sign is, again, we are looking at the disappearance of bromine. As a result, we are going to look at bromine at any time. So we'll find the slope on this curve, and that will give us the average rate. So bromine final minus initial, when you're taking this, final minus initial temperature, the time that is over here, and you'll be able to calculate the average. And then instantaneous means rate at any time. You will draw a tangent on the line and you'll be able to calculate the instantaneous rate. And initial rate is instantaneous rate at time zero. So this graph shows a better picture over here. So the average rate for 15 minutes, you are looking at 15 minutes, how much has disappeared. You're looking at the concentration, the time change was 15 minutes, and you can calculate the rate of the reaction. Instantaneous at 0.35. So if you're looking over here, you go to the concentration of 0.345, you draw a tangent over here, and then you calculate a slope around this tangent. And you can get or you guys know in your math classes, rise over run, and you can calculate the instantaneous rate. Now, if they're asking you to calculate the rate at certain time difference, you can calculate that average time difference as well, okay? So that is how you can calculate average instantaneous rate of the reaction. So if you look over here, I just want to point out one thing, that when you're calculating the rate over here, the average rate is the same irrespective of at what point you are calculating it. So the rate of the reaction remains the same for the same reaction. While this was the instantaneous rate at this concentration, that is different, right? But the average rate will always be same on this graph at any point that you're going to take. So I hope you guys made a note of it. Here, so I just wanted to point out, we are going to be doing a lab where we will be doing the iodination of acetone, and we would be using Beer's law again, and we'll be using colorimeter. So if you all remember, with the colorimeter, we first need to identify the wavelength based on the color change, and we are going to have used the same wavelength when we are going to do a reaction, and we will be able to calculate the rate of reaction and the activation energy of the reaction when we will do the lab. So it will help you make the connection with the change in the concentration with the absorption. I hope you all can remember that we had done this in our Q1. So it would be a good review using Beer's law. So now, reaction rate and stoichiometry, very, very important point to remember. Make sure you make a note of this. So we talked about rate is change in concentration over time. right? And we are going to put a negative sign when it is a rate change of the reactant over time. That is what we are going to focus on. Once again, the negative sign is just there to show that it is a disappearance. So in general, this is how a reaction looks like. These values A, B, C, D are the coefficients that you get after you balance an equation. Now, the rate of reaction, whenever the coefficient is, for the reactant, it is negative 1 over whatever the coefficient is based on the change of the concentration of A over time. Here, because C and D are your products, there is no negative sign. So what it is telling me, to equate the rates, we must divide the rate of disappearance by its coefficient in a balanced equation. So this will help us figure out the rate of reaction. Reactants go away with time, therefore we have a negative sign. So the other thing now, if you look at this reaction, we have a ratio of 1:2. So we can see that with time, the concentration of N2O5 is decreasing. The concentration of NO2 is increasing, but it is increasing at a much higher amount because it is in a ratio of 2 compared to oxygen, and there is less amount of oxygen being formed. So we can calculate this using the coefficient. So 1/2 concentration of NO2 over times. So try to do problem number 1 and 2 to help you see how you can calculate the rate based on the information that is given to you. So pause the video, solve some problems. Now, in this section, we are going to learn how to describe how reaction conditions like concentration, temperature, presence of catalyst affect the rate of reaction, right? So we all know the rate of reaction can be affected by these. But why? Why do these factors affect the rate of reactions? Right? Because if the concentration increases, there is going to be a lot more molecules that can undergo a collision. And therefore, increase in concentration increases the rate of reaction. Why? Because anything that increases the collision will increase the reaction. Very important that make sure you understand and connect it to collision. Temperature. As temperature increases, we know the kinetic energy of the particle increases. And if the kinetic energy of the particle increases, there are likelihood of more collisions that will take place. Surface area. If there is a larger surface area, there are going to be more collisions that are going to be possible within the chemical reactions. We are going to talk in more details about catalyst and catalysis later on in this chapter. So let's look at this another slide over here. What it is trying to show you, why increase in surface area increases the rate of reaction, because the number of collisions will increase. So if I take a piece of something and I powder it, if I powder it, I'm going to increase the surface area. And as a result, there are going to be more frequent collisions that will take place, and it will increase the rate of reaction. If over here, aqueous concentration, if I increase the concentration of my reactants, again, I'm going to facilitate more collisions, and as a result, I'm going to increase the rate of reaction. Now, here, look at this. Volume of the gas. So in case we are going to talk about the gases, if we decrease the volume, collisions will increase, because if I have a smaller volume, if volume decreases, collisions will increase, versus if it was in a larger volume, right? So if you are going to decrease the volume, the reaction rate will increase. So be careful with this when we are talking about understanding the difference between the volume and the concentration. And then the last, decrease in volume would increase the collision. Make sure that you understand this will only apply for gases. It will not apply for any other phase. And then the last thing that is going to affect the rate of reaction is temperature. We know as temperature increases, again, collisions will increase. Why? Because as temperature increases, reactant molecules will move much faster, and there are going to be more collisions that will lead to increased rate of reactions. Right?